we're going to be using this next brief session for highlighting, because of the level of interest expressed in the surveys and in some questions regarding hybrid models. I want to highlight a number of the hybrid models which are available to you on your thumb drives and or on the network share, the O drive, from your perspective. This is not with an eye towards providing you with a comprehensive introduction to each of those models. I do provide a systematic walkthrough of either building up these models or of kind of examining how they work on my YouTube page for several of these models. And the best point of reference, although it's not complete now and I need to add some additional models, I do have an AnyLogic example health model inventory. This is directly linked to off of the main site that I referred you to previously that has all the lectures and tutorials and model presentations, etc. The model presentation areas has some relevant material. So some of them, for example, the basic health economics model that we'll be talking about, I have screencasts associated with that. I have screencasts associated with a hierarchical model. We don't have time to build in this boot camp and others. So you might want to check that out. But more critically, up towards the top of this page is an example model inventory. This model inventory provides a subset of the models, provides sort of description of a subset of the models that I provided to you as part of this boot camp. But what you'll notice is that some characteristics of models are described. In some cases, there's links to YouTube screencasts describing, and I highlight the sort of which of the three elements supported by AnyLogic, agent-based modeling, stocks and flows, with system dynamics, in other words, or discrete event modeling, are represented. You'll notice there's quite a few hybrid methods, and those may be worth a look. But a number of models that I provided to you here are not available on here because they have they're part of existing collaborations or otherwise have restrictions in circulating them. But I provided them to you as part of the boot camp for you to look at with good faith belief that you won't sort of take them out and spread them around elsewhere. The concern there is that some of them I built with people who haven't yet sort of okayed a public distribution. So I'd like to take a look at a couple of these models, try to highlight a few of the sort of key points in the models, the key nexuses, as it were, of where the two, where several techniques come together, or other points of a special note. And I'll leave it to you folks to sort of either look at the YouTube videos which explain them in detail, or which describe the process of building them up. I'm also, of course, glad to answer questions. If people have questions and you'd like me to comment more on this at any time during this discussion, please tell me, like, I'd like to see how this is done, or could you show this? And I'd be glad to spend more time on it. The idea is to make the best use of the time, but to be adaptive to your specific needs. So I'd like to highlight a couple of these. So one thing I've mentioned several times during the boot camp, which we haven't, but where we haven't actually looked at a model that exhibits this, is this whole idea of describing agent dynamics using, in a multi-scale way, agent dynamics evolving according to stocks and flows, potentially in addition to discrete elements like state charts, other components, and then having those agents in networks. So to help highlight such a model, I'd like you to go to the O drive, and I'll do the same here. If we go to the O drive and we look at the example models, if you go to the area that says, oh, maybe it's not on there. Okay, gosh. Okay, that limits things a little bit. I normally have an area that says for sharing in class only. We're going to have to make sure that's available to you because there's some more sophisticated models there. For example, one built with an immunologist involving H1N1 flu and its propagation that includes immune system activation. Let's instead go to the CTL State variable example model. So this is cytotoxic T lymphocytes, an important component of cell-mediated immunity, and one responsible for stamping out infections once they have occurred. This example was built as a sort of a thought piece model early on in some work looking at immunoepidemiology of chlamydia, a common high-prevalent sexually transmitted infection. What we see here, well, I'll back off for a second. So what we see here is a model. It's an agent-based model. So we have, say, main class, we have an environment here. And within this person class, we have dynamics that are described by two components. And again, this is sort of more as a proof of concept than an ongoing model. I'm going to turn this off. Not pleasant, and you can tell me if I need to project more. So here we have agents that have some characteristics, and they also have dynamics described by a simple immune system model based on work done by Watars and Nowak and May, published in a book called Viral Dynamics. Here we have some number of three virions. We have some uninfected cells that are infected over time by the three virions. So this infection that occurs in those infected cells in turn end up producing more three virions up here towards the top. There's a simultaneous buildup of CTLs, so these are cytotoxic T lymphocytes that serve to attack the infected cells and kill them off. These cytotoxic T lymphocytes are built up by the presence, encountering the presence of infected cells. So they detect presence of antigen and build up some defenses. This is a very, very stylized and simple model. We have a much more extensive flu model that I'll make sure that I provide to you on that folder that was already there. So we have individuals here progressing according to dynamics described by these stocks and flows. And then we have a state chart up here which indicates whether someone is living with that. Now that may seem odd, but the idea here is that beyond a certain level of viral load, you may get into a fatal situation where the person dies. We want to be able to distinguish that situation. So here's a quiz for you. Yes. Okay. So good question. So in the system dynamics area, you're talking about these links versus these flows? Yeah. Okay. So great question. So a flow indicates a situation where we have conservation of quantities going on. So in other words, we have a flow here from X to Y. That is actually a flow in a material sense of some number of cells which were uninfected and have now become infected, and there's conservation going on. Those cells are taken out of X and they go to Y. Okay? And it's can be quantified as some amount per unit time. That's some number of cells being infected per unit time. Say per second, 10 cells being infected in epithelium, something like that. By contrast, a link indicates a functional dependency of a given formula on another quantity. So links occur to many variables here. I'll go out of full screen mode, but I'll highlight this variable new infection, for example, which computes sort of the rate of new infection. And that's given by beta times V times X. And therefore, it depends on beta on X and on V. And these links here indicate that dependency visually, that it's visually dependent on it. And in fact, any logic, and as with some other system dynamics packages, is a little bit picky in insisting that there be, if this thing depends on a parameter, depends on a state variable here, there needs to be a link from that state variable to this location of the formula so that that dependency is made clear, okay? But there's no implication of conservation here. These are functions of these other quantities. Now some of these functions end up being used, for example, in these flows, but these are ways of graphically describing formulas and communicating graphically from a level of abstraction. This guy depends on these three. If you want to see the details of how it depends on this, and this, you'll have to click on the formula. But at a high level, it communicates there is a dependency there. One of the big reasons that we articulate these links, you can think of when we look at a system dynamics model, it's been remarked before that a system dynamics model is kind of like a spreadsheet turned on its head. What do I mean by that? What I mean is in a spreadsheet, the data is obvious and present, and the links are hidden unless you turn on formula auditing or tracing in Excel, for example. Whereas in a model such as this, the dependency, the logical dependencies or links are what you see at first. And if you want to see the data, well, then you can run the model and request it, but the data is sort of one step removed. So here we have the logical structure shown. Does that make sense? Yeah. Okay. So here we have a situation where we do have both links and flows. So if we were to run this model here, we could take a look at the simulation, and we could see sort of how this operates. So here we've arranged people in what sort of network, folks? It's a ring lattice network. So in other words, people are connected with their nearest neighbors in this network. And each individual, if we go down, each individual is described by a set of these differential equations. We could kind of run an individual forward over time. And you'll notice that, well, it's finished now. I'll restart it here. You'll notice that if I go down, each individual is evolving over time in terms of their level of immune activation, their level of free virions that are present. What's notable is that I should have emphasized this. This is a non-obvious part of this model, but perhaps a key nexus. Here we have coupling between individuals, so we've seen how state messages are sent between individuals to coordinate inter-agent interactions. Here we have virions coming in from neighbors into this person's free virion stock. So in other words, the idea is that in this case it's a viral model, and so you would have virus being exposed to virus from neighbors, say in a needle sharing network or a sexual transmission network. So there'd be some amount of free virions coming in that would kick you off in the infection cycle, and then there'd be subsequent cycles of infection because of that. And so in other words, then your body would start responding. It would build up some number of cells would get infected. It would build up immune response and challenge that. So here we have individuals in a network, and those individuals are responding via infection. Folks, if we wanted to change this to be a distance-based network, how would we do it? This is a quiz. Sorry? Where would we go? If we wanted these people to be in a distance-based network, where would we go? We go to environment. We wouldn't go to person, we go to environment, because that takes care of a set of people. Okay, so we're going to go to the environment, and where in the environment? Advanced, thank you. And we could go down and we could do a layout type, do random, and and network type, do distance based down at the bottom. Boom. Oh, folks, the TAs. So apparently there's some problem opening the O drive. Could you check on that? Okay. So here we have a population. We've changed it to be located in a distance-based network. Who else needs help from TAs? So now we have a distance-based network, and we have people transmitting within the distance-based network. Now you'll notice people are disappearing over time. Anyone want to hazard a guess as to why that is? People are dying over time. So if we go up to person and we go over and check the conditions, here's another test. If you wanted to make it so that person dies when they receive too high a level of free virions, how would you do that? Anyone? What sort of transitions does AnyLogic support? Is this a message transition? A condition, yeah. So if we go to look at this, there's a condition. If the viral load is greater than a certain viral level threshold, then a person can die. Now there should be a thing here. Yes, they are removed from the population at the time that they die. So we've seen that before. So here we have a situation where individuals can persist in fighting infection to a certain point as long as it doesn't go too high, and above that point they then die. Now I'm running the other scenario here, which is called high viral threshold level, and we're running it over time, and we see someone responding. So here, I can't remember. You can go look at the oval for a person. Either I think the width of the oval is shed by or is determined by their viral load, and the redness of the oval is determined by their CTL level, something like that. And here you see successive individuals being infected, responding to it, and clearing the. So it must be the viral load is actually the redness, and the width is actually their level of immune memory. So here we see individuals retaining some immune memory over time, even following their infection. So if we were to go down here, we'll find people who are no longer infected or have very, very low levels of infection and have contained it through their immune system response, and they maintain quite high levels of immune system. So here we see at an individual level some of the dynamics going on. So this is a case, without wanting to belabor this is a case of a model where we have individuals evolving in a hybrid way, namely according to both discrete transitions, live dead, and according to continuous dynamics described by system dynamics. So any questions on that before I move to another model? No? Okay. So we're going to move to another model now. So the second model that I'd like to take a look at would be a model that's called Basic Health Economics 1. This also enjoys a confluence of both system dynamics and agent-based modeling, but it does so in a fashion that where the system dynamics is playing out at a higher level than the agents.